Today, I will discuss few important points of one important work. That work is done by my PhD scholar Prabhat Das, and this work may be, uh, maybe and surely be going to help the researchers in this field, in the field of AI and IoT. Basically, clustering. Those who are working in the field of clustering and supervised learning, they will get benefited from this work. So without wasting the time, let me share the screen and discuss the main important points. I hope you can see the screen. The title of the work is Development of an Optimal Approach towards IoT data analysis using clustering technique. So you can see this work is a combination of two important fields, that is artificial intelligence, which is a part of the clustering techniques, and IoT. And as I said, my PhD scholar name is Prabhat, and I am Dr. Bora. The defense to be conducted, main defense to be conducted tomorrow, that is 27/04/2026 at the Assam Kaziranga University. And that will be the seminar hall in the SCT building. Okay, so summary, I can say this research addresses the challenges of analyzing the massive and high velocity heterogeneous data streams generated by the IoT. So here data we are talking about is the massive in size, high velocity and heterogeneous data stream that is generated by IoT. And traditional clustering algorithms often fail in IoT environments because they are designed for the static data sets, not dynamic, right? And it lacks scalability and also require manual parameter tuning. If I say the core contribution, then the core contribution of this work is RT burst. Okay. And this RT burst stands for real-time balanced iterative reducing and clustering using hierarchies. Okay. RT burst is the main contribution, real-time balanced iterative reducing and clustering using hierarchies framework. And it extends the classical burst algorithm for which we incorporate these tasks, that is parallel chunk-wise processing to handle high velocity data. You may note that I'm talking about parallel. That way we are handling this time as well as the means high velocity data, and adaptive microcluster thresholding based on the 95 percentile of intra-cluster distances to improve robustness to noise. This point is also very important. I should tell you that this work takes around 5 years of time. This started almost in the year of 2021 and now completed in the year 25. December around, and now 26, not December, almost November and December month, and then final viva is going to be conducted tomorrow. So it takes almost 5 years of time, right? So this point, adaptive microcluster thresholding based on the 95th percentile of intra-cluster distances to improve robustness to noise. Okay, to deal with the noise, we deal with this adaptive microcluster thresholding. Then dynamic cluster count re-estimation using SSE-based elbow method with knee locator to adopt to concept drift. Again, remember, this is one important point for which we try to deal with the term means issue of this cluster count. Okay, so here it is done with the help of SSE-based elbow method with knee locator to adapt the concept. Then multi-level anomaly detection that you can consider as an application of this work. Multi-level anomaly detection that identifies malfunctions or security intrusion by analyzing cluster dynamics. So these are the main contribution. parallel chunk-wise processing, adaptive microcluster thresholding, dynamic cluster count re-estimation, multi-level anomaly detection. And main objective, if I talk about the objective, you already got that what is the problem. This is the problem statement of heterogeneous data streams, real-time heterogeneous data streams. It cannot be dealt by the common traditional algorithm as they deal with the static ones, not the dynamic. So you know the problem statement. Now, for that problem statement, we kept this objective. The primary goal was to address the limitation of existing clustering algorithms like high time complexity and lack of adaptability when applied to massive, that is large-scale real-time IoT data streams. And the specific objectives were, first one is O1, that is objective one, algorithm development, to develop and improve the clustering-based approach which reduce time complexity that can automatically and accurately determine the optimal number of clusters for large IoT devices. And that we did through parallel chunk-wise processing, thread-based, right? Then pattern recovery, that is objective two, to analyze and interpret the form clusters to discover hidden patterns and insight from both structured, that is sensor data, and unstructured, that is images of IoT data. Okay, so that is a pattern analysis part. Right, I'm repeating again, our objective two was the pattern discovery, where we analyze and interpret the form cluster to discover hidden patterns and insight from the structured as well as unstructured data. Then performance optimization is our objective three, to group similar the IoT devices into clusters to enhance the system performance by reducing latency and communication overhead in real-time data transmission. So what we are doing, we are grouping the similar IoT devices into clusters and to enhance this performance by reducing the latency, right, and communication overhead in real-time data transmission. And our fourth objective is the security enhancement, where we try to detect vulnerabilities within the clusters of the IoT devices, enabling early identification of abnormal behavior and improving the security and resilience of smart environments. So these are our objectives. I'm repeating again. First one is the algorithmic development. Second is the pattern recovery. This means pattern discovery. Third one is the performance optimization, and fourth one is the security enhancement. Now, if I say what are the research scope, future requirements, and research scope. So this thesis outlines several directions for future work to extend the applicability and robustness of the real-time burst framework. And here I want all of you to focus, because these are the works we kept open that you can consider for your PhD work, or any research work, either PhD, postdoc. Even if you're research-based masters, then you can also go for some chunk of it. First, application to smart agriculture. This work we already doing some part. Intensive application of the enhanced algorithm in precision farming to monitor soil conditions, crop health, optimize irrigation process in real time. Then stress testing under extreme conditions, conducting further studies under extreme operating conditions such as higher data arrival rate, larger sensor populations to test the framework's adaptability to highly noisy and bursty data. Then advanced representation learning, that is extending the methodology to support deep learning and auto-encoder based extraction to better handle high dimensional or multimodality data. Then edge and collaborative architecture, further optimization for resource constrained edge devices and integration within edge cloud collaborative architecture to balance computation and communication overhead. And then explainable AI integration with EXI, explainable AI to improve the interpretability of the clustering decision that is critical for trust in sectors like, healthcare, industrial monitoring. And then last, we can say about the hybrid models. You can develop some hybrid clustering models that combine the strengths of unsupervised and supervised learning paradigm. Now, these are the future scope that you guys can work. Again, I'm repeating some points, some important points of the strategy. That first one is the scalability. Okay. Here, this RT, real-time burst, maintains linear time. So that is the main advantage. And that is big O of N. Just ignore this dollar symbol, big O of N complexity, making it suitable for continuous large-scale IoT data stream. This is possible because this is parallelly happening. Okay. So parallel processing is done. That's why your this so complexity here, big O of N. Then performance, evaluating the performance with some benchmark data sets like Intel Lab RTIoT 2022. It showed that this our real-time burst achieves lower average execution time, 5.24 seconds compared to K means 5.85 seconds, and in this case 13.23 seconds. So that is good. Then, so here, that's why I'm mentioning performance is better. Then security integration, this framework, this framework acts as an unsupervised to supervised pipeline where clustering results are used as level input for training high accuracy classifiers like XGBoost that attains 0.9991 recall. That is very good for real-time intrusion detection. So we use the clustering results as a level input that we push towards for the classification tasks with XGBoost, and that is showing very good. That is 0.99, almost 0.999 recall, and that is very good, or you can say fit for real-time intrusion detection. Then practically ability means applicability. What I already told you, it can be applied in the agriculture sector or health sector. Okay. So the research included fundamental web application that we developed for smart IoT web app. We developed with Flux, Python and Flux for real-time monitoring and visualization. That is also one of our output. And then cross-domain validation beyond IoT. Beyond IoT, what happened? The framework was validated in AI educational assistant like testbed and a recruitment system, auto hire RT. So this we have done. We have validated our work, right, in an AI educational assistant, testbed and recruitment system, auto hire RT. Okay, so this works. I am satisfied as a supervisor because he's really sincere to achieve the work, and we have a lot of very good publications, including Web of Science Index, Sky Index, and Focus Index publications in journals and IEEE conferences, infringers. Okay. Then you can ask me that I, as a supervisor, I should defend. I'm planning like that because these questions, I feel that they are important, right? So because this is kind of static lecture, I'm talking with you, but you cannot ask me now. You will see the video later. So I myself, you put some question. As a supervisor, I'm going to answer this question. First, why choose bars as the baseline of our more modern deep learning based clustering? Yes, well, deep learning, like autoencoders, offer flexibility, but it requires high computational resources and retraining time. Remember, our work takes only very linear complexity, that is big O of N only, right? So it is preferred for IoT because of its lightweight and provides linear time performance and operates within bounded memory limits suitable for edge level deployment. Then how, I hope this point is clear. So we have not gone for deep learning because it took a lot of high computational resources. Then second, how does this framework handle concept drift, right? It is again a very important question. So this real-time burst employs a periodic cluster re-estimation over every 600 seconds. Okay, every 600 seconds, and it uses SSE based elbow-based SNE locator to dynamically update the number of clusters without needing to reprocess the entire historical data. So every 600 seconds, periodic cluster re-estimation is going on. For that, we are using SSE elbow-based SNE locator. So it reduces the task. It means we don't need to again reprocess the entire historical data set. We just need to deal with the real-time current data. Right? So that's why it handles this concept drift, right? Evolving data patterns. Then, what is the significance of the adaptive threshold? That is 95 percentile. You know, classical Barsh uses a fixed threshold that which fails if sensor variance changes, because here we are using IoT data. Okay, that has no limitation. That is not under any boundary. That data can change anytime, right? So that classical burst fails when the if sensor variance changes. Our adaptive threshold, right? That is, we are taking at this one. We don't consider this S1, sorry, dollar symbol, sorry. This is statistically grounded in the empirical distribution of the current steam state and making the system robust in transient noise and sensor drift. So what we are taking is an adaptive threshold. Okay, and adaptive threshold we are considering 95th percentile. So that helps the system be robust against the transient noise and sensor drift. Now, how do you justify using unsupervised clustering for security? You know, in real world IoT, pre-labeled attack data is rarely available. You don't know about the data, right? There is no such kind of pre-label attack. So our unsupervised approach proves traffic by behavior. Okay, class behaviors and clusters corresponding to a high frequency burst for, you can say TCP flag anomalies are then semantically labeled to train supervised classifier with extremely high recall. That I told you, na? Our its output of the unsupervised algorithm is being used as an input, that is level data for the executes, and that is gaining around 0.99991 high recall, right? So that's why we can say that for real-time data, this is best suitable than any other algorithm, or you can say the others means not others means I'm talking about supervised. So our unsupervised algorithm is best suitable for this type of security situations, right? So as it groups traffic by behavior, cluster corresponding to high frequency burst or TCP flag anomalies are then semantically labeled to train supervised classifier with extremely high recall. So got it, right? Next question, what are the practical limitation for real world deployment? Performance may degrade uh, in extremely massive networks. Just already. Where massive network actually millions of devices, while it works on Raspberry Pi ESP2 332 gateways, a full energy consumption benchmark for ultra low power sensors remains a direction for future. So we can do it in our future work when we get good fund, then we can go for this high massive millions of devices, right? So these are this you can consider as a limitation. I'm not saying that we are considering millions of data devices, right? Then what some may be asking that what is the novelty? First novelty, I already told you that this is this bars, RT bars we have introduced is a kind of novel of its type, because the main novelty lies in the transition from static clustering to dynamic real-time framework, specifically engineered for unpredictable nature of IoT data streams, while just a minute. Traditional algorithms like bars are efficient, they lack the adaptability required for evolving data. So this is important. So this real-time bars framework is the main novel thing that we have done. This is not like traditional bars algorithm, which uses fixed threshold, but we are uses adaptive thresholding. It utilizes 95 percentile of intra-cluster distance to dynamically adjust the clustering features tree. This allows the system to distinguish between actual data shifts and temporary sensor noise without manual intervention. Then dynamic cluster count estimation. It indicates an automated new locator based on the sum of squared errors. And this enables the algorithm to determine the optimal number of clusters on the fly as new IoT devices to join the network and data pattern changes. That is concept drift. So this new locator based on SSE, the sum of squared error is also one kind of novelty to our algorithm, and it's high velocity parallel processing because it introduces parallel chunk-wise processing mechanism, right? We are processing the IoT data in discrete and synchronized temporal chunks. It maintains linear time complexity. It ensures the system can handle high velocity streams from thousands of sensors without experiencing the bottleneck effect common in traditional IoT. Then unsupervised to supervised pipeline. That is also novel of its type because we use unsupervised clustering as a pre-labeling engine for security, right? It groups unlabeled retro traffic, identify anomalies or anomalous clusters. Then we use the cluster levels to train the high precision supervised classifier here. Attributes we can consider. So this solves the cold start problem in IoT security where labeled attack data sets are often unavailable. Then semantic intelligence for IoT data beyond simple numerical sensor reading. We proposed an approach that will handle the unstructured IoT data, such as device logs and metadata. We apply semantic analysis to extract hinted patterns from heterogeneous sources. Right? And it bridges the gap between raw data collection and actionable business intelligence. And then we can say multi-domain validation. We have validated with testnet and auto hierarchy. This novelty extends to the cross-domain implementation of the algorithm. We did not just test the model on the standard IoT benchmark, but also integrated it into testnet. Testnet is an AI-driven educational assistant that uses clustering framework for context-aware automation. Then auto hierarchy is a real-time equipment system that cluster handles. That's again the candidate profiles. Candidate profiles means we are talking about who are actually sending the resumes or CVs, right? So it cluster the candidate profiles dynamically, proving the algorithm's versatility beyond traditional sensor-only environment. So mixed multi-domain validation done. So that way you can say that our algorithms or our work is bit novel, right? Which is required for a PhD work. So I am Dr. Bora, supervisor of this PhD scholar Prabhat does. Hopefully you have gone through whole lecture and you have liked this. So if you have any comment or you want to know that what are the future possible works or any collaborative work with us, then you can definitely ask us, right? So that way, I'm going to conclude this lecture on this PhD work, development of an optimal approach towards the IoT data analysis using clustering technique. And you can find my work here in the Google Scholar. You just type by name and you will find my work. Just showing you, this is my work. Google Scholar or Scopus, wherever you will search. Right. Here you will find our papers. Okay, just search Prabhat does, then you will find this scholar's work. Okay. That's it. Thank you. Bye-bye.